in lieu of spreading it to you, I decided to take the week off, and you'll probably be happy, so you won't get my terrible illness. All right, so tonight what we're going to cover is chapter 19. This is talking about equilibrium of reactions. So we're going to learn a little bit more about reactions. We've done reaction rates. Now we want to look at what is actually happening during a reaction. So for most reactions, unlike what we talked about in Chem 112, we talked about an extreme situation with reactions where what is called the equilibrium of the reaction is far on the product side, which means that when we looked at limiting reactants and all the type of reactions that we talked about in 112, we were talking of only one specific type of reaction so that we could talk about the math instead of what was going on. But from here on out, we are going to learn a little bit more about reactions. Besides, when you react to reactants, you will get all product out until you reach your limiting reactant. That is not the full story. Reactions will always run, or not always, but typically will run in both directions. So you are going to have a forward reaction that is occurring. Once enough of the product is formed, you will actually get a reverse reaction where the product will form back into your reactants. So we have this system that is always happening. So we will always have a forward direction and a backward direction. And what's going to happen is that in the forward direction, we are going to have our reactants that are forming products. And in the reverse, our products will then be reforming our reactants. This is going to happen in all of the reactions that we are talking about in this chapter. So, reactants go to products. We have a rate at which this reaction happens. Then when we get enough products, we have products that return to reactants, which will also have a reaction rate. When the rate of the forward reaction equals the rate of the reverse-driven reaction, we are going to be at a state called equilibrium. This is where up till now in a lab you would say, my reaction's finished. It's gone to completion. No, it has gone to equilibrium. At this state, you will not see a change in the concentration of your products or your reactants. So at an equilibrium state, the reactants, concentration, and the concentration of the products are both constant. So in your mind, when you look at it, it is a stopped reaction. This is not the case. The reactions continue to go even after your reaction has hit equilibrium. So what you're getting is an equilibrium state that is dynamic. When we talked about vapor pressure, we also talked about a dynamic process in which we had molecules escaping the liquid form. When it hit back into the liquid, it would recombine into a liquid. That was a dynamic state where the molecules were always moving from liquid to gas, from gas back to liquid, but you did not see the concentration of the gas or the liquid change. This is the same definition. So your reaction is always happening. Your products are always going to reactants, reactants are always going to products, but when you hit equilibrium, the concentration of the products and reactants does not change. Okay? So that's why we call it a dynamic process or a dynamic equilibrium. Your reactions are still happening, you just don't see a change. Right? But on a molecular level, you would be able to see that change. All right. An example of one of these reactions, dinitrogen tetroxide will decompose into 2 nitrogen dioxide molecules. This is a reversible reaction, so we are going to forego our normal reaction arrows, and we will use arrows with only one side on it. So one-sided arrows, one pointing towards the products, one pointing back to the reactants. That is a key that tells you that this is a reversible reaction. All right? This one will reach equilibrium. Where it reaches equilibrium depends on the type of reaction, the exact reaction that you're working with, and the exact reaction equation that you wrote, okay? You've noticed as we've gone along, you have a balanced reaction. You can also write it in different ways. I could divide both of my coefficients by 2 and do 1/2 this and 1 of these, and I would have a completely different reaction equation. The reaction would be the same, but my coefficients are different, which means that the way that I mathematically describe each reaction equation is going to be different. So you're going to use each individual reaction equation that you get or that you write down to use your equilibrium, so they will all be separate from each other. All right, so if we want to describe this one quantitatively, we're going to be looking at the concentrations of our reactants and our products. And what we want to do to figure out equilibrium is that we're going to take a ratio of our products to our reactant concentrations. So how we're going to write this as basically as a quotient, I'm going to write first on top the concentration of my products, and on the bottom, to make the ratio, I'm going to write the concentration of my reactants. All right, so that's what I'm going to write. Products over reactants. It will always be that way. The next step to writing these is that I am going to take my coefficients in this fact. Because it's ratioing, I must know how much of each one of my products and reactants I am going to be reacting, or producing. So what I want to do is take that coefficient into account. So I'm going to put a 2 after the concentration of my NO2. So that will be squared. All right. So when I take this quotient or this ratio of these two, the product that I get from that is going to be a constant. And I'm going to write this as Kc. The C here means that my quotient here is a ratio between concentrations. So Kc is for concentrations. We're going to do a Kp as well. That has to do with pressure. So that is why we have to tell the difference. But this is going to be a constant. This is not going to change no matter what your concentration of your reactants or your products are. The ratio between them, if it is the same reaction equation, will be exactly the same. The equilibrium constant is always the same. Okay? We're going to talk about one exception to that, and that is going to be temperature. So this is constant, but it is also dependent on temperature. That is the only condition in which the equilibrium constant is going to change. So changing the concentration of your reactant or of your product will not change that ratio. It will just change where your equilibrium is going to be placed. That's the only difference. It tells you which way your equilibrium is going to go. What do I mean by that? We're talking about a ratio here. So mathematically, if the top of our ratio here is larger, what happens if this increases? What happens to our constant?
Increase.
It will increase, right? So if we have more product, we are going to end up with a higher K. And what that means is that with a higher constant, we are going to favor the products. That means that if you have a high equilibrium constant, that means that your reaction has a high yield on your product side. That means you increase the concentration of your product. That means that you have a higher yield. So in a reaction where you want a high product yield, which is in most manufacturing situations, you want to change, or not change the constant, you can't, but you want to change the conditions so that you get a higher yield, right? And you can do that by shifting your equilibrium. The constant won't change, but you can shift your equilibrium. Now, what happens if your reactant concentration is high? What happens to your equilibrium constant? It's smaller, right? Because this gets larger, it's 1 over that, so this gets larger, this gets smaller. So, pretty much when you're looking at these equilibrium constants, if your Kc is large, your reaction is going to favor your product, okay? If it does that, you have a high yield situation, right? So you want a high equilibrium constant if you are in the chemical manufacturing, well, any kind of manufacturing. You want a high yield. So on the inverse side, if you have a small Kc, you are going to favor your reactants. This is going to be a low yield situation because equilibrium, when it is reached, when that equilibrium constant is reached, that ratio in between the concentrations, that means that your reaction officially ends. The concentration of the two will not change. So, if you're in a low yield situation, you have to take extreme conditions in order to change the yield of your reaction. And I'll show you how to do that later on. But for now, we're just going to look at these. So just remembering this is ratioing. So if your product is higher, your Kc is higher. If your reactant concentrations are higher, your Kc will be lower, and you will get a lower yield. All right? So this is what we're looking for there. Okay, so how are we going to write these for a generic reaction? The one I gave you there as an example was an easy one. It included 2 gas phase molecules, so we're not seeing the breadth of all of the chemical reactions that we can do, correct? Because it's not always done in gaseous form. Sometimes we do solution chemistry. Sometimes we just bump 2 solids together and hope something happens. No, not really. So, but for a generic reaction, for a general chemical equation, what we are going to get is coefficient A, molecule A, let's say this one is a gas. Then we have coefficient small b with a solution B. Then we have coefficient small c with a solid C. That's not carbon, that is a variable. So keep that in mind. All right, so again, we want equilibrium conditions, so the double-sided arrow. Our products, small f at x is a coefficient, large X is a gas molecule, small y is a coefficient, large Y is another solution. small z is another coefficient, large Z is a pure liquid. So that would be water or mercury, something of the pure. All right, so when we compare these, the quotient or ratio that we're going to write out is only going to include gases and solutions. So when I write this out, A and B will be included, but since C is a solid, this will not be included, and our pure liquid will not be included. So anything that is in a pure state, which will be a liquid or a solid, is not included. That is because when you're talking about concentrations of pure, we are only going to be able to find that in a density situation, and densities are fairly constant even if a reaction is happening. All right, so if you have a solid sitting at the bottom of a reaction between gases, the solid is not going to take up that much space. It's not really included in your concentration because you're going to be talking about partial pressures of gases. And we never include a solid into those calculations, so we won't include them in ours as well for equilibrium. So anything in the solid or liquid form will not be included. So we're talking only about ratios of our mixtures. And you might say to me, well, a gas isn't a mixture. A gas is a pure molecule, right? What's all around us? All kinds of gas. It's an air mixture. So yes, when you are talking about a molecule in a gaseous form, you are talking about a mixture of air in that molecule's gas. So the concentration or pressure that you are talking about also includes the air. So that is considered a mixture unless you are working in a vacuum. And most of these aren't done in a vacuum, so you are going to have other gas molecules involved. So yes, technically these are mixtures and not pure. So we are going to include gases. And they will affect your pressure, they will affect your volume, they will affect your concentration. So they are part of these calculations. So when we write these generic ones out, we are going to start with X here, do the concentration, then our coefficient is the coefficient here, becomes our exponent. So we have X over X, capital Y over lowercase y as our exponent again, divide that by the concentration of A, capital A, the little a again is our coefficient which becomes our exponent, and then concentration of B, lowercase b is our coefficient. So again, we are going to, just like with our elementary steps that we did for our rate laws, we are also going to be directly using the coefficients, and they are going to become our exponents. So that is how we are going to write these out. And if we are in equilibrium, again, this ratio will be considered the equilibrium constant between those two. So that's how we're going to write these ones out. This is called the equilibrium constant expression because it expresses the equilibrium constant by ratioing those concentrations. Okay. So how mathematically are we going to determine how to use this equation in a real life situation? How are we going to use this in an example? So let's say, for example, we're running this reaction, SO2 gas is going to react with O2 gas. So oxygen gas, and we are going to create 2 SO3 molecules from that. This is our reaction that we're going to do. This is one of the examples. 19.3, I did the one that they didn't work out, so if you want to do the one that they work out, you can do that one. You also will want to do the other extra one that they gave you, and now you will have that worked out as well. So there's 2 examples that you can use. 19.3, so that's the example problems. It's on page 693. This one I do want you to make sure that you look at in the book, because if you just read the chapter, the technique for solving this equation is not in the text. It is only in these examples, and they use it to solve several of the equations or problems in this chapter. So you must learn this technique. It is very important that you get this one down. All right? So the technique that they use in this example are called ice diagrams. No, we're not talking about solid water. Ice is the initial or the beginning of each one of the stages in solving these problems. Okay, and I'll show you what the ice stands for. Let's say that we are going to start this reaction here, and we have initial concentrations that we're going to start this reaction at. The initial concentration for 2 SO2 is going to be 3 molar. The initial concentration of our O2 is going to be 6 molar. And just to be different, they are also going to start the reaction with some of our product. Since these are reversible reactions, that is completely okay to stuff some of the product in to see which way our equilibrium is going to move or where it's going to be set at. So sometimes in these, you do start with some product. If the initial concentration of the product is not mentioned in the question, it is 0. Because sometimes you start a reaction without having any product. That's kind of the point of some of the reactions, is to create the product, so why start with some of it? But in some cases, you will start with some of the product. So if it's mentioned, add it as the initial concentration. If it is not told to you in the question, the initial concentration of your product or products is 0. Okay, so that's one way to look at this. Okay, here's the first part of the ice. The I stands for initial. So when solving these, the first thing that you put underneath the reaction, you always write your reaction, and underneath each one of your reacting molecules, you put your initial concentration for that compound. So we write initial. The C in ice means change. The next thing that you want to determine is how does your concentration change when it hits the equilibrium. The last part of the ice diagram is equilibrium. So I stands for initial, C stands for change, and E stands for the equilibrium. And these are all concentrations. So what is your concentration change? And what is your equilibrium concentrations? Because if we want to use this equation here to find an equilibrium constant, we have to know the concentrations at equilibrium. So this is another thing to keep in mind with these concentrations. If we are determining Kc, these concentrations are equilibrium concentrations. You can't just stick initial concentrations in and think you're going to get a constant at equilibrium. Because in order to get an equilibrium constant, your reactants and products have to be at equilibrium. So we're talking about the equilibrium concentrations here. So this is what we want to know. What are those concentrations? And all we have is the initial. The second part in here says that, so you have these are the initial concentrations as part of your question. And the question they want to know is that the equilibrium concentration So here's our question. If the equilibrium concentration of our product, SO3, is equal to 1.4 molar, what is the equilibrium concentration of your two reactants? And that is the question they want to know. So what you're determining is at the bottom here of this chart. What is the equilibrium concentration of the SO2? What is the equilibrium concentration of the O2? I'll draw a box here so it'll be a little easier. Figure out what all these are. If I just draw it as lines, you might get a little mixed up. Okay, so here, the bottom one is our equilibrium concentration. They told us here the equilibrium concentration of our SO3 is 1.40 molar. All right, so okay, so how can we fill this in? The only information that we can determine right now is how this concentration changed from the initial concentration to the equilibrium concentration, right? If we subtract this one from this one, we will know how this has changed. Right? So it's changed by 0.4 molar. All right. So here's our change. Another thing we have to take into account is the coefficients in front. What they stand for is how much of that molecule you needed to run this reaction. So when we are talking about concentrations, we also have to take those coefficients into account. So here, the change is 0.4 molar total. But that's for two of these. So the change for one, such as this one here, the O2 has a O in front of it, the change for that will only be half of what it was for the one that was doubled, right? Because there's twice as much of this produced as there is for this that's reacted. So the change that we see across here is going to be constant. But we have to take into account our coefficients. So this one was actually, to determine the change, was 2 times 0.2, right? Because there were twice as many of those. So the change had to happen for two of those. So each one had a change of 0.2. So when we go to the oxygen here that has a coefficient of 1, the change is going to be 0.2 instead. Right? Because there were twice as many of the SO3. So the change, it's not different, it's constant across, but it's dependent on your coefficients. What about for the SO2? Which change do you think that one has? 0.4, right? Because it was also doubled. So this one would be also 2 times that 0.2. All right. The other difference is that what is happening to the reactant concentration as the reaction happens? It's decreasing, right? So the change for reactants is going to be negative. Okay? Because you want the concentration at the end to show what's actually happening conceptually. The concentration is decreasing on the reactants and increasing in your products. So your change here was positive, which is good because you added your products, and for your reactants is negative. So we're going to take 3 and we're going to subtract off the 0.4, so we are going to get 2.6 molar here as our equilibrium concentration. Here we're going to take the 6 and subtract off the 0.2 to get 5.8. So the concentration change across a reaction has to be the same. If one thing changes by a certain concentration, everything else changes by that same concentration. The only difference is you have to take the coefficients into account. All right? So if we were looking at this and x was our change, this one would be 2 times x, this would be x, and this one would also be 2 times x, which keeps the change, which is x, exactly the same across all of them. It's just for 2 of them we had to double it because of the coefficients. So that's the way that you can look at that one. The change x here is the same, only 2 of them had to be doubled. All right, so now we have our final answer there with our 2 equilibrium concentrations. So that's how we would determine that. The other thing that we can determine on here is what is the value of our equilibrium constant now? Well, the equilibrium constant is equal to the products over the reactants, as long as they're all either gases or solutions, so we have to keep that in mind, but they are all 3 gases in this example, so they will all take into account. So we will have SO3, our only product on top. We're going to square that concentration because of the 2. Then we divide by the product of our 2 reactants, which is SO2 squared times O2 to the 1. So we can leave that one off. All right? Okay? These are equilibrium concentrations. We determined those, so all we have to do now is plug those in. 1.4 molar squared over SO2 is 2.6 molarity squared times the O2, which is 5.80. These constants have units, so I do want you to carry your units through them. You notice that I put the molarity on everything. You want to follow your units and always have them as part of your calculation. So we're going to square this one here, so 1.96, and the molarity gets squared, so that's m squared now. We have 6.76 m squared for our SO2, and for O2 it stays as the 5.80 molar. Okay, why I did this part, I know you guys can all square it on your calculator and do that math, but I want to look at these units. You want to follow these. When I squared this term on the top, I also squared the molarity, so my molarity is now squared. When I squared the bottom one, my molarity is now squared. But now when I divide it out, these 2 molarities cancel out. So those 2 are gone. So now I go through and I work my math out. The answer here with significant figures is 0.0500, and this is molarity to the -1. So it's inverse molarity because this is 1 over molarity. So my constant does have a unit, and the unit is inverse molarity. All right? So does everybody see how to do those calculations now? You can do them separately, and the book tells you how to theorize your way through it, thinking about 112 math and working through how concentrations work and how they change. But the ICE diagrams does all that thought process in one chart, one table, and that's what's so incredibly useful for it, because this is the easy problem. Later on, you're going to be given less information and have to solve for more, and that's when the ICE diagrams become incredibly valuable.
Later on in like another class, right?
No, in like 20 minutes. I'm just foreshadowing to where we're going.
I'm just trying to learn as least possible.
Okay. All right, so we've been talking about the concentration and how we do the equilibrium constant for a concentration. That will not always be the case. When we talk about gases, you can also use partial pressures. So you can measure pressures and then compare those as well. So what we want to look at is how to get the constant or equilibrium constant when you are using pressures, which is going to be Kp instead of Kc. The other thing we want to know is how do these two values compare? They are not the same. So you can determine two separate constants, and you may want to switch between the two, so you're going to want to know how they relate to each other. So we're going to now have the same equation we had before. So we're going to have AA, which is a gas, BB, which is also a gas. I changed it up a little to have some gases. CC, this one is a solid. XX is a gas. YY is a gas. And ZZ is going to be a liquid again. So this is our example reaction for using pressures. Now, because a solid and a liquid does not exert pressure on a container because it is in a solid form or a liquid form, we are not going to use this in our equation either. So we're going to leave those two out again. So defining Kp, the constant, with a pressure in mind, we are going to take the pressure, the partial pressure of X, because we start with products, so we have X to the X, or P to the X. We have P capital Y to the Y over the partial pressure of A to the small a, and partial pressure of B to the small b. So this is how we are going to do it when it involves pressure. All right? So you would be given a total pressure, and you would have to determine the partial pressures and put those in. So these are going to be worked a little bit differently, but they are very similar to when you are using concentrations, only now you have to use the properties that we learned for partial pressures. Okay. How do they relate to each other? The same way that concentration has always related to pressure when we are talking about a reaction. Kc times RT is going to give us a pressure. Again, we went back to looking at the ideal gas law. PV equals nRT. When we are talking about concentration, because that's what we're comparing it to, the concentration of our gas is N over V, which of course is moles per liter. That's concentration, right? So if we solve for N over V here and here, we are going to find that equation. So the pressure here, the pressure there, here, partial pressure, is going to be equal to the concentration, that's what this is, times RT. Do you believe me there? Yes. Right? So, if this is the partial pressure of X here, then that's equal to the concentration times RT. So the constant pressure, to change that from the concentration, it's concentration times RT, correct? Now all we have to do is take into consideration all of these exponents. We do that again by using Do you remember that guy? V gas. That is equal to right? You use the coefficients for a gas, products minus reactants, and you can find V gas. And that goes right there. Okay. So again, how do we do this? Here's an example reaction. We're going to take solid calcium oxide. We are going to react it with CO2, carbon dioxide, and we are going to create calcium carbide. When we do that, we can determine our Kp equation. So for the first part of this, again, this is one of our examples out of the book. What is the equation Kp? So if we wanted to know Kp from Kc, we multiply by RT, correct? With the exponent V gas. All right, how do we determine V gas again? We take the coefficients A, B, and C. We take C minus A plus B. But it has to be a gas, right? So this one is 0, and this one is 0. What's this one? 1. So we have 0 minus 0 plus 1. So 0 minus 1 is minus 1. So our V gas is minus 1. So if we want to know the comparison between the two, it's Kp equals Kc times RT to the minus 1. So that's how we determine the V gas. Use the coefficients, make sure that they're gases, and then you subtract the products from the reactants after you add those together. The sum of the products minus the sum of the reactants. All right? And if Kc for this reaction Kp for this reaction is 25 inverse ATMs at 1020. For part B, we can determine Kc from that, right? We're going to use that reaction there. So now I'm going to use it. I determined it. Now I want to use it in the second part to find what Kc is. We know Kp is 25, so we can plug that one in. That's equal to Kc times RT. Okay, where do we find that information? What's R? Well, yeah, one of them. What is R called? The gas constant, right? So we looked that up. I already gave you the sheet of that. You'll have it on the test. You can look back to your gas laws for now. Or if you have the sheet, you have them right now. We won't use the 8.314 because this one has a pressure unit. If it has a pressure unit, we have to find the R for ATM, which I just happen to know.
You should have questions like that on the test, like what's R? You could get that.
Nobody answered when I asked though.
Were you talking about that first question?
Everybody just looked at me. I said, what's R? And everybody was like,
0.4.
here's R. So, and it's on your sheet. Why would I ask you one that's already there?
I probably still miss it.
All right, so there's R. I'm gonna put another bracket there. T is the 10, that's your temperature, 1020 K, and you want to leave it in Kelvin because there's Kelvin as a unit, so you want to keep that. The whole thing multiplied together is inverse 1 or negative 1. So let's cancel some stuff out. K cancels out, K cancels out. ATM, well, not quite yet, so we'll leave that one on there. Okay, so our temperature there, our kelvins cancel out. So we want to multiply these two together first just to simplify it. So we get times 83.69916. And this whole thing is to the -1. When we take that, 1 over that value, okay, again, we have units. You must follow your units. Anything you do to your numbers, you also do to your units. So anything that was -1 is now 1, and anything that was 1 is now -1. So our units have changed to inverse liters, inverse ATMs, moles. Right, so make sure that, again, you're following your units. Now, to solve for Kc, we want it by itself, so we're going to take 25 inverse atmospheres and divide it by 0.119475551 inverse liters, inverse ATM, mole. Okay. Inverse ATMs, it's good we took the inverse because those two now cancel out. We've gotten rid of some more units there. We divide those two. You get this big thing, and this is liters per mole. Take into account sig figs. You get 2.1 times 10 to the 3 inverse molarity, or N-1. Liters per mole is inverse molarity. All right. Oh, sorry. I'll remember to mention that. I put the wrong. So the information as before, but we are still going to use the ICE diagrams to solve for these problems. So I want to go through another example that we can do for these types. So we have a reaction. Okay, so a decomposition of a PCl5 molecule into PCl3 plus Cl2. These are all gases. It says here the equilibrium constant for the equilibrium of this reaction is 0.02. So it wants to know what are the equilibrium concentrations of all three of those molecules? All right. and it gives you the initial concentration of our PCl5 little side note there, if you see that little 0 next to the concentration, that means initial concentration. If you do not see that 0, then it is not. It is probably an equilibrium concentration or another. So the initial concentration of our reactant is 1 molar. All right, so for solving this, it wants to know, again, here's the question, what are the equilibrium concentrations of all three? So we are given the initial of our reactant. And we want to fill in our ice diagram. Initial, change, equilibrium. Okay, all they gave us was the initial concentration of our reactant. That means, since it is not stated, the initial concentration of our two products is 0. So we start with only our reactant, and it is going to decompose into these as it goes towards equilibrium. Okay, so we need to determine the change, and we need to determine our equilibrium constants. All right, we don't know any of our equilibrium concentrations, and we do not know the change that happens during that reaction. So we have to fill in and solve for some assumptions. So what we're going to do is, for the change, we know that it is identical across all of these. So what we're going to say is, as the reaction goes and hits equilibrium, we are going to have a change in concentration of our PCl5 of X. So our concentration is going to change by -X. That means that since all of our coefficients are 1, by the time it reaches equilibrium, the concentration of our two products will change by +X. So X amount of this is going to react, and X amount of these are going to be produced. So that's how we're going to set this up. Now, at equilibrium, the equilibrium concentration of our reactant is going to be 1 minus X, right? Because that's this plus this. This plus this is 0 plus X. So our concentration change is going to give us our equilibrium concentration here and also here. So these are X. So now we're going to use our equilibrium constant and our equation in order to determine these values. Because we can write an equation for this reaction with relation to concentration, because that's Kc, so we do want to do our concentrations. PCl3 times the concentration of Cl2 over the concentration of PCl5, and that is equal to this. Oh yeah, go back. For this one, I left it up here because I forgot to put the inverse there. So add that on so that later when you're looking at it, you're not like, where did that come from? That's why it didn't solve, right? Sorry, plug that in and then it'll be a little less confusing on that part. All right, so, okay, now, we want to plug in, these are equilibrium concentrations. Right now we only have X and 1 minus X, but we're going to plug those in here. So now we have X for the concentration of our two products. So we have X times X on the top. And then we have 1 minus X on the bottom. And that is equal, all right? So now we put this all in a one variable equation. So now all we need to do is solve for X. So the top then will become x squared. So now it's x squared over 1 minus x equals 0.0211. We want to get the 1 minus x out of the denominator. So we'll now have x squared equals 0.0211 times 1 minus x. Distribute that out, we will get that, right? Rearrange so that they're all on one side. We get x squared plus 0.0211x minus 0.0211 equals 1. All right, I wanted to set the equation up that way because this is an equation for solving these types of equations. We're going to use a quadratic equation. Yes?
Why is it equal to 0? Is it supposed to be 0?
Yes, of course it is. I like 1. Nope, 0. So if we have an equation in the form of ax squared plus bx plus c equal to 0, we can solve the quadratic equation. Everybody remember that guy there?
Should there be an m after all the ones?
After one of those, yeah. You mean these?
Mm-hmm.
We'll have to put that one in there. Later. All right. Yes, because we're going to have to weave that into our thing. All right. So solving for the quadratic equation, so it's ax squared, so a is 1, b is going to be so a is equal to 1. B in this one is equal to 0.0211 m, and C is also negative. All right. Yes, so that's what we have there. Once you solve for x, so it's equal to minus b. This one we're going to use plus. Squared 4ac negative Alright, so we just start to solve for this guy here. Multiply this all out and add it together. What are we going to get? M squared minus n. Over 2. Kim's not in there right, I'm gonna have to figure that one out. Well, should be him at the end. Oh, well. Square minus m, n, n. We're looking at maybe half, this has to be squared. All right. Okay, so by solving for that, okay, we have the minus version. If you want to go ahead and solve for that one, it's going to end up negative. And we can't use a negative value in concentration because in here when we plug it in, we can't have a negative concentration. So we cannot do the minus because it is B plus or minus. So you will want to work both of those out, but probably the plus one is going to be the one that you're usually going to use because we're not going to use imaginary things here. We need to use things in the physical world. So we do the positive one. So our change for x there is going to be 0.135. So now that is what x is equal to here at the end. So you have that on there. So now we know that the equilibrium concentration here for PCl3 is going to be 0.135 molar. This one is 0.135 molar. So concentration of Cl2 at equilibrium is 0.135. The concentration of PCl3 is also 135. And then we'll have 1 minus 0.135 if you do not know how to use the quadratic equation, please look it up. Yes, if you can solve it in your calculator solver, awesome, use that. On the test, you still want to set those problems up, but then you can use the solver if you know how to use the solver on your calculator. I never learned how, so I can't show you how. If you want to ask one of your friends, that'd be a good idea to ask how to do that solver. It'll save you a whole lot of time. I just do it by hand, so I do it slow method. I know my husband knows how to do it, solver, so if you really want to know, I will bug him to show me. Okay, so if you ever want to combine equilibrium equations, So if you have two reaction equations that you're working with and you have the equilibrium equations worked out, if you want to combine those ones, so let's say just like when we were doing our other reactions, you have two different steps of a reaction and you want to add those together to get the total reaction, and you know the equilibrium constant or the equilibrium equation for both of those. You can use these techniques so that you can determine a new equilibrium constant without having to redo your new equation. So if you want to combine two of them together, if you want your new equilibrium constant, so this is equation 1 plus equation 2, if you want that combined equation, what you are going to do is you are just going to multiply those two values together, right? So if you combine two reactions and you have the equilibrium constant for both of those, you just multiply the two together and you will get your new one. If it is a forward and you want the reverse, they are inverse of each other. Yes?
Is that what we just said, equilibrium equation? The last part that we just worked on, like what is the title of that?
This one here,
Yeah.
that's just working with equilibrium calculations. So it's just a version of the first one that I gave you for equilibrium when they don't give you one of the equilibrium concentration. So it's just a harder, it's just a more complex version.
Okay.
Right, so that's how you're going to combine those ones there.
English, please.
Yeah.
Lois.
The Chatelier. We've already talked about him. I just didn't put all the little tilde things on his name, but he is French or something. Yeah, it's Le Chatelier, so it's French. So he's a French dude. What we're going to talk about with the Le Chatelier's principle is that if you do not have the yield that you want on a reaction, these are the ways in which you can affect your equilibrium. You cannot affect it by rate. Rate is a different idea. Rate is how fast a reaction will happen. The equilibrium, the rate just tells you how fast it's going to get to the equilibrium. So we're not going to use any of the rate law stuff. What we want to do is we want to change different conditions for our reaction and see what happens to our equilibrium. So for the Le Chatelier's principle, wish I knew French, there are going to be three ways in which we can try to change the yield of our reaction or change the equilibrium of our reaction. Not the constant, that's always the same. There's only one of these that will actually change your concentration constant, but this is just ways in which to move your equilibrium from favoring the products to maybe favoring the reactants, or just different ways you can mess with a reaction and see what happens to it. One is by adding a concentration of one of your reactants or products. So you just change the concentration of one of them and see what happens to your equilibrium. Number two, we can change the volume. If we're talking about a gaseous solution in a reaction, we can change the volume, just like with the gas laws. Change the volume, therefore changing the pressure, because decrease in volume of a gas, what happens to the pressure? They're inverse, right? So it increases. Decreased volume, so smaller space for your gas gives you higher pressure on your gas. Just think about taking a piston inside a closed container and pushing down on the gas. What's going to happen? It's going to push back because the pressure is higher, right? So we can play with volume, we can play with pressure. For the third one here, this is the big one that can actually change your constant, and that is temperature. So if we mess with the temperature, we can actually or your pressure. Okay, concentration. All right. So these are the things we can do in order to change a reaction and look at the equilibrium. Okay, so we're running a reaction and we're going to do the first one first. So we're going to look at the changes on concentration and how that is going to change your equilibrium point. Okay, so how does this work? Your reaction is going to go. You're going to have the forward reaction, the reverse reaction, and at some point they're going to meet where the rate of both is equal to each other. That sets your equilibrium point. What your equilibrium constant does is it tells you where on that reaction that point is. If it is high, that means that it's set more to the right of your reaction, which means that it favors your products, which are the ones to the right of your reaction. If it is low, it favors the reactants, so it's set to the left of your reactant. Opposite of how I'm doing while you're looking at me. Stage left. Okay? So that's what you're doing when you're looking at a reaction. The left favors the reactants. If the equilibrium is set to the right of the reaction, it is favoring the products. So what we're doing is trying to move that point. Okay. So if we want to change the concentration, we need an example reaction here. Let's say we're going to take some carbon. We're going to react that with some CO2. And we are going to produce some carbon monoxide gas. 2 of those. All right. So we hit an equilibrium between these guys, and all of these species exist at equilibrium. So they're there in some concentration. Okay. Varying the concentration of the carbon isn't going to do much for us because it's a solid. That's not going to affect our equilibrium at all. So changing a solid does nothing for us. So the concentrations we want to change are the ones that are in our equation, right? So we want to change either the gas on the reactant side, the carbon dioxide, or we want to change the amount of carbon monoxide. So let's say in the first example here, we are going to increase the concentration of the CO2. And what that means is we just open the container and we inject more CO2. So now we have a higher concentration of CO2. What is that going to do to our equilibrium? Okay, well, our equilibrium has to do with CO squared over the concentration of CO2, and that is a constant, right? So if we increase the CO2, this is going to shift to get back to equilibrium. So we're talking about, here we have CO2, and now we have a whole bunch of this. For the equilibrium, it is going to shift from being to the left, which favors, again, our reactants. That equilibrium is going to shift towards the right, favoring making more product, because to equal that back out to equilibrium, it's going to run the reaction in the forward direction because it wants to use up that CO2 to make the concentrations of CO and CO2 equal again. Not equal to each other, but it wants them to be at equilibrium just like it was before. So it's going to shift the equilibrium from left, favoring that heavy amount of CO2, to the right, which is going to create more product, evening out those two concentrations again. Okay, so do you see why it shifts that way? So on the other account, let's instead inject our reaction with CO. Now we have a heavy concentration of our product. So now this becomes huge, or it increases. To keep this constant, this must also increase. So in order to increase the reactant, we're going to favor a reverse reaction where we take a bunch of that CO and convert it back to CO2 and carbon. So the equilibrium in this case is going to move from right, favoring the product, back to the left, favoring our reactant. Okay, so that's how concentration can and being a solid, remember that guy is not considered. I shouldn't even write anymore. Words, English. Okay. Okay, for Le Chatelier's principle, what's going to happen to our equilibrium if we now change the volume of the container our gases are in? So now what we're going to do is we want to play with this container. So we're going to have a container, closed container that has a gas in it. And again, there's our piston, so we're going to push that down. Let me see if I can make these equal sizes. Nope, failed miserably. Oh well, you'll see the point. Okay, so we're going to decrease the volume. We're going to push down on that thing. When we decrease the volume, we're increasing our pressure. Okay? More gas in a smaller space, more collisions, higher pressure. Okay, so this is what we're going to have. So we have a gas here. Let's say that the gases that are in there, our original reaction here with our dinitrogen tetroxide, decomposing to my 2NO2 molecules. All right. Remember those reverse guys. All right, so how does this concept work? What we want to do is we've changed the conditions of our reaction. We have pushed this down, we have decreased the volume of the gas, it has less space to take up. So to reach back to its original conditions, to try to alleviate this increase in pressure, what it's going to try to do is minimize the number of gas molecules that are in that space. So when you have an increase in pressure, the concept here for Le Chatelier's is to minimize the number of gas molecules in that smaller amount of space, hoping to relieve some of that added pressure. So let's look at our equation. If we look here, if we have the non-decomposed gas here, the N2O4, we only have one molecule of it. It's larger, but there's only one. Here we have two NO2s, so every time this decomposes, we now form two molecules. So if we decrease the volume here, increasing the pressure, which way do you think the equilibrium is going to favor? Which way will it go? Towards the one molecule, right? To make less space, or make the less space available, have less molecules in it. So for equilibrium, the shift is going to be from the right to favor the left. So we're going to get more of the reactants. So if you have a reaction in which you'd rather actually keep your reactant, or you decide that you have too much product and you want more of the reactant back, you just make the space the reaction has to go smaller so that it favors now the reactant side. Now if you want to make more product, what you'll want to do instead for this reaction is you want to increase the volume. Go ahead and make that liquid. Okay. So from the original there, that looks almost the same. Okay. We give it more space. Increase the volume. We decrease the pressure, and our equilibrium point is going to shift now towards our product. Because with less volume, a decreased pressure, it's still trying to get back to that equilibrium point where it was at the beginning here. So it's going to want to fill that space with more molecules. So now we're going to favor that product. So not only do we have to take into account how our quotient works, how our equation works for our concentration, we also need to take into account our coefficients again to tell us how many molecules of our gas are we creating in these reactions. So we also want to take that into consideration.
So let's say you maximize the amount of molecules, like the reverse.
Yeah, so when you're working with the higher pressures, you minimize, and when you work with the decreased pressure, there you go. You want to maximize your number of gas molecules in there. So that's why it favors our product side now, moving towards the right, or our product side. This one now is going to have to depend. When we're adding temperature to a reaction, the general trend for reactions is that if you increase the temperature, you increase the rate at which the reaction goes. It can be considered a catalyst. Increasing temperature makes molecules move around at a higher energy, getting more molecules over the activation energy, allowing more reactions to happen. So in general, you do want to increase the temperature if you want to increase your yield. Now, one thing you have to take into account with this is just a general overall statement for reactions, but you also want to know what type of process do you have. Now, if your reaction involves heat, so it is an exothermic reaction that's already giving off heat, would really adding more heat be a benefit to that reaction? You're not going to get a higher yield. You increase that temperature, you're going to drive that reaction back to the reactants because you're adding heat. Now, how does that work? Let's say we have this reaction here. Okay, so we're going to be creating N2 plus O2 gives us 2NO, so we're making nitrous oxide, and the heat of this reaction, our enthalpy, is positive 182. Oh, I did the wrong one. Keep that for later. No, don't erase it because I'm going to use it for the other one, but I just realized that's the endothermic. Don't erase it. You're just going to make an arrow to it later. Don't. I hear you all. Don't do that. Oh, no. All right. So sorry, this one is our exothermic. Releases heat. So another way that we can write this guy is by including heat. Since we're talking about changing temperature, we want to include our heat generation into our equation. So heat now becomes one of our products as well, because we are producing heat through this reaction. So now we can look at it the same way we did the concentration one. If in this fact we use the common knowledge and say we're going to increase the temperature, we're going to be adding heat into our reaction. So with an increase of heat, with a reaction that we're trying to create heat, we are going to make a favorable side for our product. So what we're going to actually end up doing with this theory is that we're going to take our equilibrium and we're going to force it from right to left. So it would have been here, now it's going over here, and we're creating more of our reactant. So in this case, going against better judgment, or more informed judgment than just going with the common knowledge, if we decrease the temperature, we're actually helping ourselves out, because now we're leaving space for more heat to be created. So if we lower the amount of heat, we're going to drive the equilibrium in the opposite direction towards our products. So you also have to take into account what types of reactions that we have. Are they endothermic? Are they exothermic? So same thing's going to hold true. With our endothermic, now you can write it again. All right. So endothermic means that you need to put heat in. So you need to provide heat here. So since it needs to be provided, it will actually be on this side of the reaction as one of our reactants now. Okay, so this is where the common knowledge would be good. Increase the temperature, increase the amount of heat, drive your equilibrium from left to right. Decrease your temperature, you'll drive it back in the reverse, back towards the left. There is a very rich man because of Le Chatelier. Mr. Haber developed the Haber process or Haber cycle, which creates ammonia. Right, so looking at this reaction here, would you increase the pressure to get your product, or would you decrease the pressure, or would you just run it at room temperature if you want a higher yield?
Decrease.
Right? Increase or decrease?
Well, yeah, I would go increase then.
Increase, right? If you want to favor a system with less molecules, you increase the pressure, decrease the volume, right? Less room favors less molecules. Move towards the two. So in order to create ammonia, all you have to do to make the process yield more, which we use tons of it a year, so we must yield lots of it. The Haber process allowed us, by increasing the temperature of the process, to yield a higher amount of ammonia. Now, this is also an exothermic process. So would you want to lower the temperature or increase the temperature? That's a very good idea from what we've been talking about. But we also have to take into effect one more thing. Lower temperature means slower reaction. So we also have to take into account the rate of the reaction. If we slow it to too low, we actually end up decreasing our yield. So there's a lot more factors, but yes, by Le Chatelier's principles, we would want to run this at a lower temperature. But since it would move at a snail's pace, even with increased pressure, they decided to actually leave it at a high temperature, high pressure setting. You have to sometimes take some of these for granted for working with a better process. But that's a very good example of how these principles are used to actually create a better system. I can do this. Okay. One last deal about our reactions is that another way that we can look at reactions is just by using a constant other than Kc. So at equilibrium, Kc is equal to the concentration of the products over the concentration of the reactants. Both of these at equilibrium. That's how you get your equilibrium constant. Now we can also get a quotient called Qc, where you take products divided by reactants, but these are not in equilibrium. So we can study equations outside of the equilibrium conditions, but we have got to use a different constant, which in this case we're going to use Qc. Okay. So you can study outside of equilibrium. Now, what we want to do is keep in mind that all reactions are always moving towards equilibrium. That is called spontaneous movement. It moves towards your equilibrium always. So if we take a quotient outside of equilibrium and we know the equilibrium constant, we can compare the two and we can see which way our reaction is moving. Is it running in the forward direction or is it moving in the reverse direction? So if QC is greater than KC, QC is favoring your products, and KC being lower may not be. So if you're looking at QC and it's going towards KC and it's much larger, that means that your reaction is actually running in the reverse at this point, because it's trying to lower the amount of your products, correct? Higher QC means it's higher product concentration, so it's moving from the right towards the left to get to equilibrium. The opposite is true if your quotient is lower than your equilibrium constant. The equilibrium constant, if QC, is lower, that means the reactant concentration is much higher than it is in QC or KC, and that means that your reaction is running in the forward direction, left to right. So reactant to product. So that's another last way that we can look at equilibrium and have that reaction, this equation, work outside of equilibrium conditions. But keep in mind, QC, non-equilibrium. KC, equilibrium. Okay, so this is a specific, this equation is exactly the same, but this is a specific condition where your two rates are equal, forward and reverse, and your equation or reaction is at equilibrium. Right? So that's chapter 19.